Hi everyone, and today's lecture is going to be the final lecture regarding finite impulse response finite filters, and this is going to be some design examples as to how we can design these filters as of such. So our first example here is that we need to the requirement for this design is going to be a 10 Hz FIR filter, and then we're going to have to compare the performance of a suitable moving average filter and an 11 order Hamming window based FIR filter in satisfying this application. And we're going to be assuming a sampling frequency here of 100 Hz. So for the moving average filter, this basically means we need to make sure that we have the number of terms that is required to be averaged. And the zero crossings in this case will be at 10 Hz, because capital omega denoting these zero crossings is equal to 2 pi on n, and we can rearrange this so that we can get n equal to f of s being our sampling frequency divided by fc, which is going to be our cutoff frequency. So as such, n is just going to be 100 divided by 10. So in this case, because we know that n here is going to be 10, we basically know we can use a 10 term moving average filter in order to design for this filter in particular. The difference equation is just going to be 1 divided by 10 from x to the n plus x to the n minus 1 going all the way up to x to the n minus 9. Remember, n here is the shift is 0, and n minus 9, if you consider from 0 to 9, these are 10 terms. So that's how you end up getting the 10 terms here, and you have the 1 divided by n on the outside. The spectrum for this is basically going to look like this, where the Nyquist frequency is going to be at the dead center here, and the sidebands here for each one of these averaging terms is going to be mitigated as we keep on going towards the center here. So that actually is the end of the design of a moving average filter. We just need to calculate for what is n and where the zero crossings are, and then we just use the generic equation of 1 divided by n multiplied by x to the n, x to the n minus 1, and so forth, all the way up to x to the common n minus capital N. And that is basically our difference equation that is required for any moving average filter. The next filter that we will require to be designing is the Hamming Window FIR filter. Typically, when we say we need to design a window FIR filter, you're normally given a window equation denoted as W of n for any question that may require this. So the first step that we do here is that we need to figure out what is going to be the ideal frequency characteristic. So in this case, we're using the ideal low-pass filter here, and we'll be using a rectangular form of it. The associated time response for this, because this graph is in frequency, is given by this equation here, which is basically our sinc equation. Once we have our sinc equation accordingly, and you are required to memorize this because sometimes it does not come into the questions, the second step is that we need to truncate n. We need to truncate the response to n samples. And the reason why we choose n equals to be an odd index is such that we want to make sure that the sequence is going to be symmetric about a center point. So in this case, because we're going to say n here is equal to 11, that means the center point is going to be at 0. We're going to have 0 to minus 5 and 0 to positive 5, so that covers our 11 terms accordingly as well. In determining h of n, we had the ideal low-pass frequency filter response, seen in the last two slides, given by h of n is equal to 2 multiplied by fc divided by fs, sinc of 2 pi n fc on fs. We then, because we have h of n here, and we know the range of common n going from -5 to positive 5, we need to calculate all those values from n equal -5, n equal -4, go all the way up to n equal positive 5. We don't need to do all 11 values because this is a symmetrical sequence, so we just only need to calculate from -5 to 0 and then it just reflects accordingly, as we can see here. Because -1 and +1 will have the same index, -2 and +2 will have the same index, and so forth as we keep on going. So that will give us our h of n sequence. That is the first thing we require in order to get the filter equation for the Hamming window. Step 3 would be that we have the W of n equation that was given to us, and we calculate W of n for all the n indices, so being from n equal to -5 to +5. Similarly, like h of n, we don't have to do all the values. We just do from -5 to 0, and then we reflect the values accordingly. So for illustration purposes, remember, -1 here and +1 will have the same values, -2 and +2 will have the same values, and so forth as we keep on going. Step 4 is where we finally find the window indices for the FIR filter, denoted by HW of n. So we take h of n and w of n, and we multiply straight across for each one. We don't need to do all 11 because basically both sequences have been symmetric, so we just need to from -5 to 0, and we just reflect the result as is. So h of n here, sorry, let's go back one more. So that means the -5 value here for h of n will multiply by the -5 value here for w of n, and similarly the -4 here will multiply straight off where we put -4 here. The -3 for h of n multiplies by the -3 of w of n, and so forth. So hw of n will end up into this result here. Because the n terms are 0, we can ignore those because they don't contribute anything towards the filter equation. So now that we have hw of n here on the right hand side, we can now formulate our filter equation in terms of z. And that brings us to step 5. This filter equation in terms of z is going to be an anti-causal filter transfer function. So each one of those terms there, because they are from n equal -4 to n equal +4 in this case, that represents the z delay index that we'll be calculating for, or that we have calculated for. So the -4 index is basically z to the -4, and we put the value of the index there. Same thing with the -3 index, we put the value of the index here, -2, -1, and so forth. And the indices reflect accordingly for positive and negative values. We aren't finished yet, because this is an anti-causal filter. We need to make it causal. So step 6 is where we write out the causal filter transfer function, and such that we delay it by 4 samples. So that comes like if we multiply the entire equation by z to the -4. And as of such, we now have the causal transfer function as required. And this basically brings us to the end for the design of a Hamming window FIR filter. In plotting the answer, which you are not required to do, this is just for illustration purposes, we see that the magnitude response is given by the red line, and the phase response here is given by the green line. And if we incorporate the ideal low-pass filter here by this black dotted line, we can see where our cutoff frequency and our responses would be accordingly for 10 Hz. Please note that because this is a FIR filter design, the phase here follows a linear fashion. In comparing between the magnitude, the moving average filter and the Hamming window filter, we basically can see here that the Hamming window filter tends to do a somewhat better job than the moving average filter in particular. And this actually can be seen here as well if we zoom in into the magnitude response. The Hamming Window filter has better attenuation than the moving average filter, as we can see here. So that brings us to the end of this FIR filter design example lecture.